Chemical properties of S-block elements is their ability to react readily with dilute acids. Both Group 1 and Group 2 are highly electropositive metals, meaning they lose their valence electrons very easily. When these metals come into contact with dilute acids such as hydrochloric acid or sulfuric acid, they undergo a vigorous chemical reaction. During this reaction, the metal displaces hydrogen from the acid, producing a salt and hydrogen gas. This is one of the most common reactions used in chemistry laboratories to demonstrate the reactivity of metals. The image uses magnesium as the main example. Magnesium is a Group 2 alkaline earth metal and has the electronic configuration 2008-2, which means it has 2 valence electrons in its outermost shell. Since these 2 electrons are relatively loosely held, magnesium can lose them during a chemical reaction. When magnesium is placed in dilute hydrochloric acid, it reacts to form magnesium chloride and hydrogen gas. The balanced chemical equation shown in the image is Mg plus 2HCl MgCl plus H. This equation tells us that one magnesium atom reacts with 2 hydrochloric acid molecules to produce 1 molecule of magnesium chloride and 1 molecule of hydrogen gas. The upward arrow next to H indicates that hydrogen is released as a gas. To understand this reaction more deeply, we must examine what happens at the atomic level. Hydrochloric acid dissolves in water and separates into hydrogen ions and chloride ions. The dissociation of hydrochloric acid can be written as HCl H+Cl. When magnesium is added to the acid, each magnesium atom loses its 2 valence electrons. The oxidation half reaction is Mgn plus 2. This means magnesium is oxidized because it loses electrons. The magnesium atom becomes a positively charged Mg ion. At the same time, the hydrogen ions present in the acid gain these electrons. The reduction half reaction is 2H plus 2EH here. 2 hydrogen ions each gain 1 electron and combine to form a hydrogen molecule. Since hydrogen ions gain electrons, they are reduced. Because oxidation and reduction occur simultaneously, this is a redox reaction. The image clearly illustrates this electron transfer. It shows magnesium changing into Mg after losing 2 electrons, while hydrogen ions accept these electrons and combine to form hydrogen gas. This transfer of electrons is the fundamental process that drives the reaction. After magnesium loses its electrons, the resulting Mg ions combine with the chloride ions already present in the solution. The ionic combination is Mg plus 2Cl MgCl. The product formed is magnesium chloride, an ionic salt that remains dissolved in the solution. Therefore, after the reaction is complete, the test tube contains a solution of magnesium chloride along with bubbles of hydrogen gas escaping into the air. The image identifies 2 products of the reaction. The first product is magnesium chloride, which is an ionic salt. It consists of magnesium ions and chloride ions held together by strong ionic bonds. The second product is hydrogen gas. The image describes hydrogen as a colorless, flammable gas. Since hydrogen is much less dense than air, it rises upward after being produced. One of the easiest ways to recognize this reaction in the laboratory is by observing the formation of gas bubbles. As magnesium reacts with hydrochloric acid, numerous bubbles appear on the surface of the metal. These bubbles consist of hydrogen gas being released continuously. The image also highlights an important laboratory test called the pop test. If a burning wooden splint is brought close to the mouth of the test tube containing hydrogen gas, the gas burns rapidly with a characteristic pop sound. This pop sound confirms the presence of hydrogen gas. Because of this property, the pop test is commonly used in laboratories as a simple identification test for hydrogen. The image also states that the reaction is exothermic, meaning that it releases heat. During the reaction, the formation of new chemical bonds in magnesium chloride releases more energy than is required to break the bonds in hydrochloric acid. The excess energy appears as heat, causing the temperature of the solution to increase. The reaction between magnesium and hydrochloric acid is generally steady and controlled. However, more reactive S-block metals react much more vigorously. The image includes an important trend showing magnesium, calcium, barium with an arrow labeled reactivity increases down group 2. This means that the chemical reactivity of group 2 metals increases as we move downward in the periodic table. The reason for this increasing reactivity is related to atomic structure. As we move down group 2, each element has one additional electron shell compared with the element above it. The outermost electrons become farther from the nucleus, and the inner electron shells create a stronger shielding effect. As a result, the attractive force between the nucleus and the valence electrons becomes weaker. Since the outermost electrons are held less strongly, they can be removed more easily. Therefore, the metal loses its two valence electrons more readily, making the reaction with acids faster and more vigorous. For example, magnesium reacts moderately with dilute hydrochloric acid, producing bubbles of hydrogen gas at a steady rate. Calcium reacts more rapidly than magnesium because it loses its two valence electrons more easily. Hydrogen gas is produced much faster, and the reaction is noticeably more vigorous. Barium, which lies below calcium in group 2, reacts even more vigorously. Hydrogen gas is evolved rapidly, and the reaction releases a larger amount of heat. This increasing reactivity is one of the most important periodic trends in the chemistry of alkaline earth metals. Although the image uses hydrochloric acid as an example, group 2 metals react similarly with many other dilute acids. For example, magnesium reacts with dilute sulfuric acid according to the equation Mg plus HO MgSO plus H. Here, the salt produced is magnesium sulfate instead of magnesium chloride, but hydrogen gas is still released. Similarly, calcium reacts with hydrochloric acid according to the equation Ca plus 2HCl cockle plus H. Barium reacts in the same way, Ba plus 2HCl Bockle plus H in every case. The general pattern remains the same. Metal plus dilute acid salt plus hydrogen gas. This is one of the fundamental reactions studied in inorganic chemistry. The reaction with acids also demonstrates the concept of the activity series of metals. Metals that are above hydrogen in the activity series can displace hydrogen from dilute acids. Since all group 1 and group 2 metals are highly reactive and lie well above hydrogen, they readily replace hydrogen ions from acids, producing hydrogen gas. The image also includes an important laboratory safety warning. Hydrogen gas is highly flammable. When mixed with air, hydrogen can ignite easily and may even explode if exposed to a flame or spark. Therefore, reactions producing hydrogen gas should always be performed carefully under controlled laboratory conditions. The image also reminds students that acids should be handled with protective equipment. Hydrochloric acid is corrosive and can damage the skin, eyes, and clothing. Safety goggles, gloves, and laboratory coats should always be worn when performing such experiments. It is also important to note that group 1 metals react with acids even more violently than group 2 metals. For example, sodium reacts extremely rapidly with hydrochloric acid, 2Na plus 2HCl 2NaCl plus H. Because sodium is more reactive than magnesium, this reaction is much more vigorous and can become dangerous if not carefully controlled. The behavior of magnesium demonstrates another important chemical principle. Magnesium achieves a stable electronic configuration by losing its two outermost electrons and becoming Mg. The hydrogen ions achieve stability by gaining electrons to form neutral hydrogen molecules. Both the metal and the hydrogen ions move toward more stable electronic arrangements during the reaction. S-block metals react readily with dilute acids because they easily lose their valence electrons. Using magnesium as an example, the balanced equation Mg plus 2HCl MgCl plus H shows that magnesium reacts with hydrochloric acid to produce magnesium chloride and hydrogen gas. During the reaction, magnesium is oxidized by losing 2 electrons, while hydrogen ions are reduced by gaining those electrons to form hydrogen gas. The reaction is a redox reaction, is exothermic, and releases noticeable heat. Hydrogen gas can be identified by the pop test, and the salt formed remains dissolved in the solution. As we move down group 2, from magnesium to calcium to barium, atomic size increases, electron loss becomes easier, and the reaction with acids becomes increasingly vigorous. This behavior clearly demonstrates the close relationship between atomic structure, electron transfer, periodic trends, and the chemical reactivity of the S-block elements. Characteristics of S-block elements is their strong metallic character. Metallic character refers to the tendency of an atom to lose one or more electrons and form positive ions, also called cations. Unlike nonmetals, which generally gain electrons, metals readily lose their outermost electrons because these electrons are weakly attracted to the nucleus. The S-block elements, which include the Group 1 alkali metals and Group 2 alkaline earth metals, possess the strongest metallic character in the periodic table because they have only 1 or 2 valence electrons that can be removed easily. As a result, these elements readily form positive ions and participate in numerous chemical reactions. The image explains that S-block elements easily lose their valence electrons and form positive ions. This behavior is the defining feature of metallic elements. Whenever an S-block metal reacts with another substance, the first step is almost always the loss of its outermost electron or electrons. After losing these electrons, the atom becomes positively charged because the number of protons becomes greater than the number of electrons. The image first uses sodium as an example. Sodium belongs to Group 1 and has the electronic configuration 2008-1. This means sodium has only 1 valence electron in its outermost shell. Since this single electron is weakly held by the nucleus, sodium can lose it very easily. The process is represented by the equation. Na plus E. This equation shows that a sodium atom loses 1 electron and becomes a sodium ion. Because 1 negatively charged electron has been removed, the sodium atom now possesses 1 more proton than electrons and therefore carries a positive charge of +1. The image next shows potassium. Potassium also belongs to Group 1 and has the electronic configuration 2088-1. Like sodium, potassium has only 1 valence electron. Its ion formation is represented by Kk plus E. Potassium loses its single outermost electron and forms a potassium ion. Since potassium is larger than sodium, its outermost electron is even farther from the nucleus and is held even less strongly. Therefore, potassium loses its electron more easily than sodium, making potassium more reactive. The image then introduces magnesium, which belongs to Group 2. Magnesium has the electronic configuration 2-8, meaning it has 2 valence electrons. Its ion formation is represented as Mg plus 2e. This equation shows that magnesium loses 2 electrons from its outermost shell. After losing these 2 electrons, magnesium becomes a Mg ion, carrying a positive charge of +2. Unlike Group 1 metals, which lose only 1 electron, Group 2 metals lose both of their valence electrons to achieve a stable electronic configuration. The image also presents calcium, another Group 2 element. Calcium has the electronic configuration 2008-2. Which again means it has 2 valence electrons. Its ion formation is Kk plus 2. Like magnesium, calcium loses its 2 outermost electrons and becomes a Ka ion. After losing these electrons, calcium attains the stable electronic configuration of the noble gas argon. The image summarizes this behavior by explaining the difference between the two groups. For Group 1, the process is, Group 1 loses 1 electron m. This means every alkali metal loses 1 electron to produce a positive ion with a +1 charge. Examples include Li Nana KK, RB, RB, Cs, Cs. All of these ions have a single positive charge because only 1 electron is removed. For Group 2, the image shows Group 2 loses 2 electrons m. This means every alkaline earth metal loses 2 electrons and forms an ion carrying a +2 charge. Examples include BBMG, Kaka, Senior, Ba. Every Group 2 metal forms a doubly charged positive ion because 2 valence electrons are removed. The image also explains why S-block elements lose electrons so easily. Several important reasons are listed. The first reason is that these elements possess only 1 or 2 valence electrons. Since there are very few electrons in the outermost shell, removing them requires relatively little energy compared with removing electrons from elements that have nearly full outer shells. The second reason is their low ionization energy. Ionization energy is the minimum amount of energy required to remove the outermost electron from an isolated gaseous atom. S-block elements have among the lowest ionization energies in the periodic table. Because very little energy is needed to remove their outermost electrons, electron loss occurs readily during chemical reactions. The third reason shown in the image is the weak attraction for the outermost electrons. The valence electrons are located relatively far from the nucleus, especially in the heavier S-block elements. In addition, the inner electron shells shield the outer electrons from the positive charge of the nucleus. As a result, the attractive force between the nucleus and the valence electrons becomes weak. Since the attraction is weak, the electrons can be removed easily. The fourth reason given is that after losing electrons, the atoms achieve a stable noble gas electronic configuration. Atoms naturally tend to move toward the most stable arrangement of electrons. Noble gases possess completely filled outer electron shells and are extremely stable. For example, sodium has the electronic configuration 2,081. After losing 1 electron, sodium becomes 2,008. This is exactly the electronic configuration of neon, which is a noble gas. Similarly, magnesium changes from 2,082 to 2,008, again achieving the stable configuration of neon. Calcium changes from 2,088 to 2,008, which is the electronic configuration of argon. Thus, losing electrons allows S-block elements to reach highly stable electronic arrangements. The image also presents a simple sequence explaining the relationship between these ideas. Low ionization energy, easy electron loss, positive ion formation, strong metallic character. This sequence summarizes the entire concept. Because the ionization energy is low, electrons are removed easily. Easy electron loss produces positive ions, and the ability to lose electrons readily is precisely what defines strong metallic character. Metallic character also explains many other physical and chemical properties of S-block elements. Because they lose electrons easily, they are highly reactive, especially with water, oxygen, chlorine, and acids. Because they readily form positive ions, they produce ionic compounds with nonmetals. Because they possess loosely held valence electrons, they are also excellent reducing agents, donating electrons to other substances during chemical reactions. Metallic character also increases as we move down both Group 1 and Group 2. As we move downward, additional electron shells are added to the atom. The atomic radius increases, the shielding effect becomes stronger, and the attraction between the nucleus and the outermost electrons decreases. Consequently, electron loss becomes even easier. For example, in Group 1, lithium 9 sodium 9 potassium 9 rubidium 9 cesium, the metallic character increases steadily because each successive element loses its outermost electron more easily. A similar trend occurs in Group 2. Beryllium Nash, magnesium Nash, calcium Nash, strontium, and barium again. Metallic character increases because larger atoms hold their valence electrons less strongly. The formation of positive ions is one of the most important concepts in chemistry because it explains why S-block elements react with nonmetals to form ionic compounds. For example, Na plus Cl NaCl, Mg plus O MgO, Ca plus 2Cl cacal. In every case, the metal first loses electrons to become a positive ion before combining with a negatively charged ion. The metallic character of S-block elements arises because they possess one or two loosely held valence electrons, low ionization energies, and weak nuclear attraction for their outermost electrons. As a result, they readily lose electrons during chemical reactions and form stable positive ions. Group 1 elements lose one electron to produce M ions, while Group 2 elements lose two electrons to produce M ions. After electron loss, these atoms attain stable noble gas electronic configurations, making the process energetically favorable. The ease with which S-block elements lose electrons is responsible for their strong metallic character, high reactivity, ability to form ionic compounds, and their important role as reducing agents in chemical reactions.